A couple of technical notes. For ARMA data, you got to t-set the data. For ARMA models, you got to t-set the data. And no, I don't think that's true. So yeah, it's t-set the data. So ARMA models only work if you t-set the data. Mostly because we've got to use the lag operators, and the lag operators only work when we t-set the data. So to do a dynamic forecast, you can see the option here. It's use that comma dynamic, and essentially you tell it when you want it to start pretending there's no data. So we're going to start in 2008 of Q4, which is the last quarter of that data. And we want to pretend that that data doesn't exist. So this will be a true dynamic forecast. Looks like we're doing, I'm going to use the 1-1 data, so go back. What did we do? Yeah. All right, so let's do the 1-1 model. I'm going to change this to all right, so let's run our model again, which we've already run. And our dynamic prediction, and I think it tells us, let's see, I should say something about this in the data set. Yeah, so it tells us it's a dynamic prediction here, and then when we're assuming that the data stops. So this kind of prevents us from, again, kind of cheating. It's not really cheating, but it prevents us from taking advantage of the fact that we're predicting something that we know the outcome of. Right? If we know the outcome of tonight's game, we're probably going to be a lot more confident in our bets. So here we're eliminating that possibility. All right, so let's see it go. Just go. So what do we see? We see that the one step ahead forecast and the dynamic forecast are exactly the same where the data exists, which is here. You can kind of see it following. Can you see the dots? So we're in between the dashes of our one step ahead forecast is the dots from our dynamic forecast. So the forecasts are, the fit of the model is exactly the same. The fit of the model is exactly the same. The difference is, in a dynamic forecast, after that prediction period, so what happens here? So the fit's going to be the same, and then after that prediction period, there's data there. And what the regression is going to do is going to try to match those data. And that's why our fits, even with a holdback sample, is going to be pretty good. What a dynamic model does is, by specifying that option, is it prevents us from doing that. It's going to pretend that that data doesn't exist, and then we can see how accurate our forecast would have been if we didn't know that data existed. So we can zoom that. Hopefully that makes sense, because it doesn't make any sense to me. It doesn't make any sense. All right, so 1-1 and 1-1 dynamic. And again, this is just kind of a zoomed in picture. You see the difference? It's real subtle. I should use a different marker than the dot. But what happens is that this is kind of the cheating one, where it's going to follow the trend of the data because it's kind of peeking in the back of the book and saying, oh, that's where the regression goes. The true dynamic forecast doesn't take advantage of the fact that the data is still there. So our prediction is not nearly as good as we would have liked it to be. And this is the reason this prediction is so bad is because the only independent variables we have are lagged sales. Once we have no more lagged sales, right? Once the data ends, we can't have predicted lagged sales anymore. So what happens is it kind of reverts to whatever was going on in these previous, what was this model? This was a 1-1 model. So we're going to have one lagged error and one lagged sales. So it goes back to kind of whatever trend was happening in those last two periods here. So it's trying to follow the trend. Notice it starts from there and then it does that. So if we have independent variables, again, like price and monthly dummies, the fit will be better. So again, what we're trying to do is improve on an existing model and not necessarily use ARMA models. Again, look at your ARMA model or look at this model here. There are no independent variables. So it's only lagged sales or lagged error terms or some combination of both lagged error terms and lagged sales. So the point is that if we add these components, this ARMA process, to a model with independent variables, perhaps a model that wasn't predicting very well, then we'll be able to improve that model. So let's try that. All right. So this is kind of the difference between peaking and not peaking. Essentially what we say about these ARMA processes is that they're mean reverting. It's basically going to revert to kind of the mean of what's going on here, and then just follows it there. So ARMA processes are, any forecast is good for short-term forecast. So we don't normally like to forecast more than, at least I don't like to forecast more than a couple of years. So after that, there's just too much that can go wrong, as well as the models just don't predict that well. Streams have been reached on your account. What does that mean?
It means it cuts you off.
Is that the university account? Let's see. Oh, the game's over. What was the score?
Kansas City won 29-20. It's on the bottom.
Oh, I was looking at the top. Kansas City won. Good. All right, let's see, we got some line data in here. Actually, we can look at that. Let's see, wine. That is very funny. Let's see, we've got incoming there. All right, so here's a model that we're pretty familiar with. We got a time variable, which is date. We got our monthly dummies to account for seasonality. We got a nice big fat R squared, adjusted R squared. Pretty decent looking model. I don't think anyone would complain about this model. But as you can see, it's a crude forecast. So I called it a crude forecast. And let's see, I don't know why. Yeah. It's not bad. Looks okay. You didn't complain much about that. Let's see, predict error. Let's check out the residuals. Again, classic serial correlation. We have a pattern in the errors. When we underpredict, we tend to underpredict again. When we overpredict, we tend to overpredict again, and then underpredict again. And so we're seeing this clear pattern in our residuals. We can test for serial correlation. But let's check out the autocorrelation and partial autocorrelation. Yeah, so we're seeing kind of a decaying nature there. And let's see, when does it start oscillating? It starts oscillating, I guess, after this third one. Second one, then it starts going back and forth. So kind of clear signs of serial correlation in our error terms. All right, so remember we got 4-week ending data, so when we T-set it, we gotta be specific about what the periodicity is. It's not true monthly data. Nielsen data is not true monthly data, it's 4-week ending data, so we use the option delta 28 days here. And again, you gotta T-set your data in order to be able to use the ARMA processes and the lag operators. It looks like our data goes from week ending December 18, 2004 to week ending April 2nd, 2011. So. Praise doesn't really do anything other than correct through transformation, tries to correct with serial correlation. What we want to do is actually use the serial correlation to help us improve our models. Because what serial correlation represents is some persistence or cyclicality in the data. And praise just tries to correct for it. We don't necessarily, we want to correct for it, but we want to use that information. And it's not really what we're doing here. All right, so let's see. Different.
Thank you.
All right. It looks like it's the same data set, so I didn't have to close it. Okay. OLS. As predicted. Again, not bad. We're checking the residuals again. We did all this stuff. Yeah. All right, so let's move on. We know we're going to reject our white noise test. Yep, reject the null hypothesis that residuals are white noise, concluding that serial correlation. Lesson 1. Factor variables are not allowed in our ARMA command. Which means we got to go back to the old school method, which was what? What did you say?
Right.
No, we still want to use ARMA. We still want to use an ARMA model. But do you remember how we constructed dummies? We have to use tab gen. So tab month, gen month, what that does is, do we use tab gen in 580? Yeah, so what that does is literally construct the set of monthly dummies. The set of monthly dummies. So it's going to be, if it's month 1, it's going to be 1. If it's not, it's going to be 0, and so on and so on and so on. So we need to include the dummies in there because our ARMA command, doesn't like factor variables, which is strange. Okay, so we could still use our ARMA process. How's that for iterations?
I just don't know.
That was cool. Okay, let's go back to the command. Oops. Time, income, and then we got our monthly dummies 2 through 12. So we can use this dash in our regression command. So we don't have to put month 2, 3, 4, 5, 6, 7, 8, 9, 10. Stata will recognize that you want to use the monthly dummies from 2 to 12. And so that's somewhat of a savior. What was our iterations? How long did it take? It only took 93 iterations. 94 if you include the first one, which is 0. And that's not bad. Like I said, that's not necessarily a bad thing. Also notice what's missing from our regression output. I should have pointed this out earlier, but R squared, yeah. There's no R squared. Again, this is a different process than ordinary least squares, so R squared isn't really defined for these ARMA processes. So you got to use the Wald chi-squared statistic is equivalent to your F statistic. Remember the F statistic in, let's run the OLS and make sure. Reg, and other stuff isn't wrong. But in OLS, look how much quicker that is. In OLS, we get the R squared, but we also get the F statistic. And the F statistic was that test that says the null hypothesis is that all of your independent variables are equal to 0. So that F statistic is the result of this hypothesis test, that beta 1, beta 2, beta n, that all of your independent variables equal 0, that your model has absolutely no explanatory power. The alternative hypothesis is that at least one beta is not equal to 0, that the model does have some explanatory power. So similar to the F statistic in our ordinary least squares regression, the chi-squared statistic in our ARMA process has the same kind of interpretation, except we don't get a formal R squared. So the chi-squared statistic is similar in that The null hypothesis is that all of our independent variables equal 0. The alternative hypothesis is that at least one of our independent variables is not equal to 0. We got this chi-squared, Wald chi-squared statistic of 975. We don't know what that means, but we can look at the p-value. And the p-value soundly rejects the null hypothesis that our model has no explanatory. So treat that Wald chi-squared statistic equivalent to an F statistic in a typical ordinary least squares regression. All right, so some technical aspects. Let's see what this looks like. Distance. HL is for eligibility. This is kind of your internal outbreak. But here are our ordinary least squares coefficients, and then here are our ARMA coefficients. Your lag coefficients. And again, notice we get an R squared for our OLS. We don't get an R squared for our ARMA process. We can, however, so basically I ran that specification. Looks like I'm running another specification. I'm running an ARMA 3.2. Now these are a little bit more common. So again, now I'm just playing with different specifications. Can I look at the coefficients, see if they're changing much? Look at your autoregressive and moving average components and see which ones are significant. I'm not sure what's under there. So there's p-values or t-values? Command is t-stat, so those are t-statistics. So if we go to our autoregressive moving average component, okay, not significant, not significant, not significant, not significant. That's our autoregressive component. Not. We switched the model from a 4-3 to a 3-2, and we've got not significant, not significant, significant, borderline, and then not significant. So again, it looks like we've over-parameterized the model. Our model's too, we don't need all of these things. So we're going to continue to trim it down. We can look at, we're going to specify another one. This is going to be a 2-1 model. All right, so here's a 2-1 model. Getting a little bit better. Now our autoregressive component for the first period lag is significant. The second one is not significant. Our moving average component is still insignificant. So again, we could trim out, we could probably trim out one of the autoregressive components and see what happens. I'm not sure what I did here. Now we're just going, yeah, that's exactly what I did. Trimmed out one of the autoregressive components left in the moving average component. All right. Now, we've got highly significant AR1 component and a highly significant MA1 component. So our T-stats are nice and big, 9 and -3. So this looks like the better model. We could use our information criteria, which I know we all love. I don't like them either. So I told you, like training wheels, you use them kind of in the same way. You're scared of what you're doing. So again, smaller is better for the information criteria. Akaki's getting smaller, bigger, and bigger. Bayesian is getting smaller, bigger, so it looks. This is telling us to go with what, 2-1? No, 15-1-3 is the smallest, and 15-6-1 is to go with the 3-2 model. But we saw that a lot of those coefficients of the ARMA process were statistically insignificant. So this is another example, yet again, of where I would not follow the advice of my information criteria. I'd stick with kind of the results of the regression and say, again, that I don't like information criteria. All right, looks like we're going to stick with the 1-1.